As let's begin. All right, can you guys see my screen? I should probably keep the chat open. Is anything blocking the screen or is it fine? It's all good? All right, nice. Okay, so hello, I am Rohit and I am the AI lead. And today we're going to be talking about some, basics of machine learning that we're going to be using in the project later in the semester. And you guys are going to get to implement this stuff hands-on. We'll start next week with an example so that you guys can see how the code, all fits in together into one bigger picture. But before that, we do need to go over some basic ideas so that everyone's kind of on the same page. And yep, so without further ado, today first we're going to talk about what ML is briefly, even though it's like been a couple of weeks since we started. We're going to talk about why it is important to even bother to learn about ML, because we have actual algorithms, like manually written algorithms and code that can be used to achieve tasks, but like, why use ML to do the same thing? So we're gonna talk about that. How is ML used? That's like the crux of what we do in Pioneers. And then the math, it's not terribly intensive. Don't worry about it. It can get intensive if you want to go further. Happy to talk about it, but not for our purposes at the moment. We're going to talk about the model as well, and how everything strings together into constructing a solution to the problem that we discuss. And ooh, I can use the pointer. Okay, and then we will just like summarize everything in a bigger overall context. So that is, yeah, let's get this out of the way really quick. I used the same picture of me last semester, but yeah, I'm Rohit. I'm the AI lead here at BigTh AI. I'm a machine learning major. I'm a junior equivalent here at UMD. I've worked with machine learning and deep learning in a previous internship with an AI product firm, including a problem that's similar to what we're going to talk about today. And so that's where like I learned a lot of contextualization of what I learn as the theory, and that's what I'm trying to share with you guys today, so that we can all try to use that. And then I have done some independent research, and I've done like a 5-month DL specialization with Andrew Ang of Stanford University, and that was excellent. That taught me a lot about manual implementations of these algorithms. And then finally, I am a seeker of the business context, and that's you guys are going to figure out what that means in a bit. But I do try to emphasize how we can apply something that we're talking about. So, oops. All right, I want to ask you guys. Yes, the Andrew Ng. Yep. What is ML? Does anyone want to hazard a guess or an opinion? In the chat or on your mic? Does anyone want to have a crack at it?
Does it have to do with machine learning?
That's a pretty good guess. Oops. I would probably say that you're like uh I don't know. It's something that we need to figure out. It's mysterious. So learning and generalization, learning and generalizing behavior and qualities from information. All right, that is a pretty good answer, and it is sort of like that. It is trying to figure out an underlying pattern that we can. Yes, word machine broke. We're trying to figure out some sort of underlying pattern. We're trying to learn from something that's there and bring it to something that we don't know for sure. That's like the core underlying principle of machine learning, and that's what we're going to be seeing later on. So there's like 3 broad types of machine learning. One is supervised learning, meaning when we are given a whole set of data, we are trying to identify the link between what we call the features of that data and the label. So we get a bunch of information about like someone's demographics, and we're going to try to figure out or maybe estimate like how credit, how risky they are in terms of paying back the credit. That's an example of a supervised learning problem, right? So we're given data and we're trying to find the link to the, like, some sort of label, some sort of answer. Unsupervised learning means we don't provide it that answer in its training, but it can still group together data and try to identify patterns that the human eye might miss. So that's unsupervised learning. And then reinforcement learning. This one's really exciting. It's basically when you have a model learn in real time, working with actual data as it comes in instead of being fed in a data set that's been compiled and collected beforehand. So, and reinforcement learning is like most commonly used in games, and now people are starting to use it for other things like, you know, stock price prediction, stuff like that. Um, there's two broad types of ML problems. One is classification, where we learn from the data to make a prediction that falls into some sort of discrete bucket, right? You know, like rainy or not rainy, or you know, this person is going to watch this show or isn't going to watch this show, and or will the stock rise or fall? It's a binary bucket there. Although it can have more categories, well, that'll just be multi-class classification. The second type of problem in ML, broadly studied right now, is regression, which means you are not trying to discretize something. You are just trying to put it, give it a value. You're trying to give it a continuous value, like estimate the price of this home, right? Given all this information about the home, you know, the size of it and the location, and like there's going to be a bunch of information. You predict what numerical value is going to come out of it. And here's another one: what will our sales on this product be, right? So that's not something you can say yes or no to. That's going to be that's going to get you fired. So that's what the main kind of machine learning problems that are out there. That didn't make sense. All right, the second part is why machine learning, right? Why are we moving towards machine learning? It is predictive, and it helps us like decode the future in a way. It's like technology's superpower at its finest so far, because we study previous data and we can get really accurate about what's going to happen next. That's something that, you know, the human mind can do, like to some level of intuition. And the algorithms that we write right now aren't really like designed for the future, but an ML algorithm can be transferred, and that's called, you know, there's things like transfer learning and all that. But you can basically take its current understanding and move it to the future. It's scalable as well. ML thinks in vectors, matrices, tensors, which is basically a way of combining a ton of data into one like packet. So that's how it thinks. That's how it processes that information, and it can draw like insights at scale if needed. And that's why, you know, in big data analytics and stuff, you see a lot of deep learning, machine learning going in, because those are like millions of data points. You can't get a human mind to figure that out. That's going to be nightmarish. And it's autonomous. With ML, we don't need to tell it exactly what to do. We just need to give it a sort of, you know, start and finish, and then it figures out how to get to the finish point. And that's like the magic of ML. Whereas in normal code, we would have the starting point, we would have to provide the how, and then it would calculate the end product. Here, we're giving it the start and the finish, the start and the end product. It figures out everything in between, and that's why it's so interesting, I guess. Where is it being used? Some, you know, pretty common places: financial services, government, healthcare, retail, manufacturing, and transportation, to name just a few. But there's a ton more, and machine learning is like all over the place. There's so many different kinds of models out there. It's going to be nuts to try to talk about them all in one meeting, but this is basically just some of the applications. What are some skills that we need as aspiring machine learning engineers or data scientists? We need our ML concepts, right? And that's like the mathematical algorithmic understanding of it. We need our data science, right? We need to know how to collect data, how to manage it, clean it, and prepare it for processing by a model. And then we need our programming skills. Um, like I like this isn't the biggest part of machine learning. Like usually most people coming in would be like, all right, I need to be incredibly good with my program. Most of the stuff is Googleable, and that's how you get around this. You have to get comfortable with Googling, Stack Overflow, and looking up the documentation of these libraries, because that's where you're going to be really versatile when like a new library comes out. You need to be comfortable with finding things on the fly. We're not we as uh, people who work with ML, we don't sit and learn a library all at once. We just know enough to keep rolling, and that's like that's something that I struggled to grasp when I first worked on an ML project. But that's basically, yeah. How is ML used? All right, so here's where everything begins. All right, we have a client giving us a problem. The client says, I run a bank. I have a ton of customers for my credit card. I need a solution where if I give it a customer's information, it's going to tell me whether they're likely to attrite. You being the data scientist, the ML engineer, you say, got it. And what is your operational definition of attrition? And that's really important because you're trying to understand exactly what they mean before you make assumptions. And I actually made this mistake a couple of days ago when we were trying to work out something for an example to show you guys. But this is a really important step, and it's what paves the way forward for the rest of the process. The event that they will stop using our credit card and stop doing business with us in the next 3 months. So that's just an example, right? Yeah, in the actual world, it could be in the next 6 months, it could be the next week, but you just have to get that clarity out of the stakeholder, and that's the client. All right, so get us in touch with your database management team and we can get started. And a few years pass. That is totally not a jab at how long clients take to turn around with the actual problem. But yeah, they'll give you the data, hopefully. And here's just like a really simplified version of an actual data set where you have the customer ID, the join date, the age, gender, and then you have a tried it, whether they actually left or not in the past. And your goal is to do this. You're trying to make something that's going to predict whether, given that information, someone's going to leave. So that's the goal here. So does anyone want to guess what kind of ML problem this is? Remember, we just had it a couple slides ago. Supervised learning and classification. That's exactly it. Those are the two key key terms. So structure learning, supervised learning. It's a binary classification problem with only two alternatives. Either they're going to attrite or they're going to stay in the next 3 months. It can be both unless you're like a quantum mechanics major. But that's why it's best solved with structured learning, because we do have that label, we do have that information in the database. So what we're going to do, and this is what Shanil talked about last week, we're going to do some exploratory data analysis, EDA. And that basically means we're going to drop a bunch of charts and graphs and figure out what the data looks like, what the correlations are, what the distributions are, whether there's any outliers, missing values, so on and so forth. And essentially, the goal of this phase, right, is to identify all your features. In this case, it would be the first four, right? Customer ID, join date, age, and gender. And then the label, which is the answer that we're trying to get our model to learn by the end of the process. And that's going to be this last column here, which is whether they left or not. Understand patterns and correlations in data. So that's this part, which is basically trying to, you as a human, you are conducting analysis to get some high level insights so that you'll be able to process the data better in the next stage, which is data cleaning. And yeah, so the next part is you're going to know what problems exist and you need to try to like anticipate how you're going to solve it. You're going to try to come up with a strategy to address it. And then you actually have to like process and clean the data. You can just look at it and be happy. But
I could add something.
Yes, go ahead.
So to the previous slide, just for yeah. So remember when we renamed the survive column name in the very first meeting to label, and I told you you'll eventually know why we did that. Yeah, this is the reason, because survival in that case was our answer, so to speak.
Pretty much. So that's why we take what we're trying to lead it to and then call it label. So that's exactly it. All right, so the next stage is feature engineering. Some people, treat it as a part of data cleaning. Some people regard it as its own thing, and it's really important in machine learning. A little less so in deep learning, but this is what makes or breaks a good model, and it's basically how you adjust it. Oops. All right. Yeah, it's basically how you adjusted it. Right. So right off the bat, I'm gonna do this one, and then I'm gonna ask you guys something in the next slide. So right off the bat, I know, for instance, that customer ID might not really affect whether they leave or not. No one's gonna come in and say, "Oh my God, I'm unhappy with my serial number." Like they don't care. They're the customer. Um, so you don't need that piece of data, and you don't want the model to think that that might be important. So you're just gonna chuck it out of your data set. The next thing would be the whole date, right? You have the day, the month, the year. It doesn't really make sense to get the day and the year when you're trying to figure out if someone left, because the day and the year keep changing, but people still keep leaving, right? But there might be, and if you don't know, you leave it in. If you do know, you take it out. That's kind of the underlying thumb rule. But there might be a correlation between the months and whether they left or not. Like, some people might be leaving, I guess, towards the end of the year for some reason. It's really hard to say without the actual data, but you don't want to take chances and take out something that might be helpful. So that's when you leave something in there. All right. Can be encoded. Right. So most data is, you can put it into two categories. One is categorical data, and then the other is numerical data. And like, if I have any friends in here who do data science, like the 320 class, there's more, but just to simplify it for these purposes. Uh, so if you have male, female, other, you can take that and give it a number. You're indexing it so that the model, which cannot read this kind of data, it cannot read categories, will be able to understand the number that's coming in. And yep, so there's just some general rules of thumb in feature engineering. One is you drop irrelevant columns. Right off the bat, you can tell that customer ID doesn't help. Second thing is combine, divide, or convert columns into something that's more usable. Something like hint, hint, if you have hourly rates and then daily rates of pay, right? You might want to think about turning those two independent columns into something that's more useful, like how many hours a day they're working through division, right? So that's like an example of how you might want to manipulate the data set to your advantage, to the model's advantage. And the third thing, oh no, this thing is covering it. Oops. All right. Yep. Encode your categorical values into numerical ones. And then usually we do something called scaling, which just helps when you're trying to get the model to perform better. But we will not go too deep into that as of now. But yep, those are the three big things. Now it's your turn. You're trying to predict someone's health insurance premium. All right. And you see that the data set has something called a has pet column. Would you drop it or keep it, and why? Does anyone want to have a crack at it?
Maybe keep it.
Keep it. Why?
Because you're not sure if them having a pet or not will change the outcome of if they drop, if they have the premium or not.
All right. All right. So when you don't know the exact link, it's safer to keep it in there. Suppose that you do go in. Oh, wait, before I get to that, there's a couple others. Only if they have allergies. That's interesting. Allergies, that's definitely something that people go to the doc for. So keep it, keep it, keep it. Um, this is great. You guys are on the right track. All right. Who was it who just said they, like, we don't know if there's a correlation?
Oh, I did.
Jeffrey. Okay, cool. So based on what Jeffrey said, if we did find out that there was a correlation, then we would need to identify if it's positively correlated or negatively correlated. That's something Chanel talked about last week. But here's another angle to it. What if allergies What's AF? Right. As far as you know, is
Yeah,
that
just as far as I know.
uh, all
I'm
right?
not a health expert, but I thought allergies were hereditary
Are
rather than.
they? Is that true?
I
I
really don't know.
did not know this. Interesting. That's something we can check out. But people who have a pet, yeah, it has to do with how often you have a case. So people who have a pet usually take the pet out for a walk, right? And walking is some sort of guaranteed minimum exercise. And that's something that like at first glance might not pop out, but that's what like the whole data analysis part can reveal to you, and then you can decide whether you want to keep it or not. Some insurance is screened to see if you have aggressive dog breeds. Wow. Right, so that's basically the risk assessment, right? And that's a factor. Poor dog breeds that are classified as aggressive, very sad for them, but um, if the statistics do point in that direction, then it's a factor to consider. If they also live in a bad neighborhood that they walk in, do you want to like elaborate on that? I'm not sure what you mean. Daniel,
Like, if it has a high crime rate, I would assume.
like maybe it's unsafe. All right. That's actually, yep. So that would be taking it one step further and saying people who might have a pet might go out to walk their pet, and then they might be in a dangerous neighborhood. So that's a pretty good yeah. And COVID, yep, good stuff, you guys. All right, so we're gonna move on to the math. Are there any questions so far before we get to this next part?
I have a question about like the correlations and stuff.
Yes.
Like, does it matter like knowing what the correlation is? Does that matter?
It does. It does. Because correlation is like a continuous. It's not just a yes or no. It's kind of a how much. So it is important to measure that. And one of the things that Shanul showed last week was this heat map, which had like the different colored squares. And it is definitely important to use that in feature engineering.
Oh,
If
thank you.
Yeah, no, you don't need to thank me. So Caleb says if this were automated, you know, would it be dropped? It would most likely, because it takes another level of intuition. But since we do have the tools of analysis, we can identify there might be a link. So this is good stuff. All right, so something from sixth grade, you guys, in the math. We have a variable x, and we are trying to get to this value y. What is the most basic function that we learn in like approximately sixth grade? Does anyone want to guess? Yay. Okay, good stuff. All right, so y is equal to mx, all right, which means we're multiplying it by some number that later we realize is the slope when we plot it. And then we're also adding a value to it, which later when we plot it, we know is the y-intercept. So that's going to be a visual representation of this abstract function where we have two parameters, right? If you think about it, what can we control to change this function? What are the two things? M and B. That's exactly it, right? M, which is something we can multiply, and B, which is something we can add. And that those two things can change how the line looks. So perfect. All right. So if you think about it, machine learning itself is a function, even though it's like, much more complex than that, where you have an input and you're trying to figure out the output. And trying to figure out why the output is what it is. That's really the overall goal of ML. So this is how, like we could, this is just another name for feature and label. We call it X and Y when we actually take it into the machine learning process. But really it's mapping the features as the input to a label as the output. And the features in our case would be the joined month, age and gender, and we would have dropped customer ID. And then we're trying to figure out if it's a 0, why it's a 0. If it's a 1, why is it a 1? So that on a piece of unseen data, the model is going to be able to guess more accurately. In other words, we have the feature and the label, right? We have we can classify our data into training, X and training Y. And that's what we're going to learn from. The X would be all the features in the data set, and then the training Y would be the label. And this is called scene data. We do let the model look at the actual labels in this and try to figure out how to guess the label more accurately, right? So the first thing it does is it makes a prediction. It's like a shot in the dark, and then it checks that prediction against the ground truth. So given a bunch of info, it guesses maybe that the person left, but in fact the person stayed. So it makes that comparison, and then it has to do some sort of internal update. And that's how humans learn, right? Because when we make a guess, we find out it's wrong, there's some sort of internal rewiring in our brains that happens, so that we remember next time that this is not the case. And we're going to look at exactly how that works. Not exactly, but like to a good degree of depth, how that works. And then we take this understanding of this model into some test data. All right. So we're evaluating it on like a test set of features, and it has to give us a label, and we're going to check if that is correct or not. We're going to check it. The model's not going to check that. The model only checks it in training, because that's when it actually knows what to do and what to change to learn. But yep, that is the whole process of seen and unseen data training and testing. Are we good so far? I'm going to assume that's a yes. All right. Right. So basically, this is what's happening. We need something to take an input, and we predict a 0 or 1. What do we have in math that does? Yeah. Okay. Yeah. The dictionary is in fact, we had a dictionary on one of the other slides, but yeah. All right. So luckily, math is way ahead of us. We do have something that takes an input and then gives us something between a 0 and a 1. And that is called the sigmoid function. Oh, by the way, you guys, if you don't already use Desmos, you really should. It is so good. It's like so nice. You can design any function on it that you want. And I even made like a whole basketball on it once, but yeah. So this is the sigmoid function, and given any X, right? Any real value for X, it's going to compress that into a value on the y-axis between 0 and 1. And it intercepts the y-axis at 0.5. So anything less than this, you can round down to a 0. Anything above this, you can round up to a 1. And we do this round. That was your 11th grade pre-calc final. You had this in pre-calc, this function?
It was the Desmos Fine Art.
Wait, did you?
With like the Lemma Scott. I don't know how to pronounce it, but it's like the fancy rows functions and stuff, where we had to like draw something with like the math.
On this or something similar?
Yeah.
That's cool. That is really cool. Yeah, that's really cool, man. Yep. So this is asymptotic. If you guys, kind of want to get technical about it, it never actually becomes 1. You can see that gap, right? It never reaches 1, but it just gets really, really, really close. So that's the sigmoid function, and we like to round it. All right. So just in summary, that's the sigmoid function. All right, that's like the scale is from 0 to 1 at the top, 0 to -1 at the bottom. Same on the left and right. We take any real value of X, and that's like the domain of X. And then we compress it into a value between 0 and 1, exclusive, and that's going to be the range. So like, why are we using this particular function? We need that binary outcome. In our case, we need to know if the customer left or if they stayed. So we need that finite range to sort of like bring, just, you guys get it. All right. There's another thing that I want to mention. In the middle of the sigmoid function, it is approximately linear, right? So that's why this is so helpful in something that has to do with probabilities and guessing the chance of someone leaving. That's because in the middle it is linear, but it gets closer and closer to like the bounds 0 and 1 without ever reaching it. But that's like, not important for us. But if you want to go further, you can look into why that is. All right. So the model, how are we going to put it all together, right? We have the sigmoid function, which takes one input, that's the x value on the x-axis, and it gives us one output. But how can we give that multiple inputs to get one output? That. And I say logistic, not so regression, because we're not using it for regression. If you recall, regression is making a continuous prediction. We're using logistic regression for classification. So that's like the kind of misnomer. But the most common application of log reg is to classify things into two categories. But yep. Logistic regression. We have this part figured out, right? And that's the Greek letter sigma, and we give it an input, and we expect an output that's between 0 and 1. But we have multiple inputs, and these are the features, right? They could be the age of the customer, the join month, and all of that. So all of those are the inputs. How do we convert all of these into one number that we can give to the sigmoid function? That's where we do something called a weighted sum, which is basically we assign each input a certain weightage, a certain importance. Oh, like we don't do it, the model does it. And we add all of those up. And that gives us one single number, right? And these weights are basically the equivalent of the m in the linear equation, where we can multiply and we can change how the equation looks by changing the value of m. The same way we can change how the result is going to be with these values of w. That's what the model has to tweak. And then there's another parameter, which is also analogous to the y-intercept in the linear equation, which is the bias. And that's just another thing that it can use to try to arrive at its final answer more accurately. And as it makes mistakes, these are what it updates. It updates its weight matrix, and it updates the bias value. Like, any questions so far? It's not easy to get it at first glance. Are we good with this?
I just wanted to clarify something. So
Yep.
you said after we get the output from the sigmoid function, we round it to either 0 or 1, correct?
Mm-hmm.
Yep, because you said it was the sigmoid function is exclusive of 0 to 1.
Yes, it is exclusive of 0 and 1 because it's asymptotic, but we do want to round it because we want to do a classification between two categories.
Correct. And is there a certain range that the weights take in terms of numbers? Like, can it be any real number?
Normally, yeah, it can be. It can be any float, but we usually have some sort of regularization to prevent them from exploding all the way up or being really, really tiny. And that's something that, that's like exploding gradients, vanishing gradients, but those are like some advanced problems. All right, are the weights the same? The weights are not necessarily the same. That's up to the model to decide how much importance to give each input. Suppose that the age is important in determining whether someone leaves the customer, someone leaves the bank, but maybe the join month turns out to not be important. Then this weight would be like 0 or something really small, but then the age weight would be pretty high. Does that make sense? Is it always the summation of xi, wi? Yeah, so you're giving each input a weightage, which means you're multiplying it with that input's value, and then you are summing all those up. That's how you get that one number that you can then pass into the sigmoid. Otherwise, you'd have like 3 numbers, and there's no way to run one sigmoid function on all those. If the machine automatically adjusts the weights and the bias, what are the parts that we control ourselves? Would it be the algorithm that adjusts the weights and biases based on the feedback or something like that? That's perfect. That's such a good question. And yes, you're onto something with that. We're going to get to that in a couple slides. But yep, that's kind of what we have the power to do. Well, yeah, once again, weights, those are the ones that are multiplied. Bias is the parameter that's added, and these are the ones that the model can control by itself. The sigmoid is what we use to get the final answer, and just summarizing these as equations down below for mathematical formality. So yeah, how does this algorithm learn to predict correctly? That's what the whole it has to mess up. It has to mess up in order to figure out what the right weights and biases are that lead it to accurate predictions. And it over time it assesses its mistakes and it adjusts those weights and biases until it reaches a configuration where it's like the best it can be. And that's what we're going to see in the next slide, but that's basically the whole process of optimization. Yep, awesome questions. Yeah, this is good stuff. Okay, optimization. This is where, step one, it has to check its prediction. It makes a guess and then it sees if the prediction is correct versus the actual ground truth of that data point. It said yes, and maybe the truth was they didn't leave. So it has to check that first. And then it has to compute the difference between those two using a defined cost function. Now, some of these can get really scary and long and stuff. This particular algorithm, the logistic regression algorithm, uses logarithms in it, and that's why they call it the log loss. But don't worry about it, it's abstracted for us thankfully with scikit-learn. But if enough people want to do like a more detailed under the hood implementation of logreg by the end of the semester, we can definitely work our way towards that. But we're gonna like just use libraries, as Sammy said. All right, so it tries different weights and biases over lots of data, tries to find out which has the lowest cost. Again, the cost is its error rate almost. You can approximate it to that for conceptual understanding. So the algorithm, and this is what Sungmin was asking. Did I say that right? My bad. Is it? Okay, cool. So that's what Sungmin was asking about. These algorithms are called the solvers or the optimizers, and we have the ability to decide which one it uses. We can also decide what loss function or what cost function it uses to assess how off the market is. And that's what we can control as the machine learning engineers. But in the libraries that we're going to use, like there's some default values and default functions in there. So we don't have to worry about it, but we can if we wanted to change those things. Some common ones include stochastic gradient descent in logistic regression, but more on that another time. So this is like a really simple version of what actually happens, but this is like a 2D plane representation where it tries out a ton of different weights and biases. It plots the cost over different configurations, and then it sees which one was the lowest, and it decides on that as the like that's the best it can get with and so this is where, like in calculus, you have the concept of a local optimum and a global optimum, or like a minima. That's where this comes in machine learning. And if you get into like the math and the algorithms of these models, then you're going to try to find ways to address like the model could have settled here at this configuration of weights and said, this is the best I'm going to get because this part is a hill, but it didn't know that the part like here goes lower. So that's like that's the whole challenge that we address with calculus rears its head again. Yep. Anything that we can answer on this slide as of now, or anything so far that we talked about? All right. That's cool. Looks like things are going pretty smooth. Okay. All right. What does it mean by label? So the label is the actual answer to the question. In the data set, we are given a bunch of customers, and then we are given whether they actually left or not. And our goal is to train a model to like look at that data, and then on a new customer, the model tries to guess if that customer left or not. Is it fine if we're a little confused but understand the overall concepts? Like, yeah, that's totally okay. If that confusion isn't letting you sleep at night, we are happy to spend more time discussing these things. But this is just like a broad overall understanding, and it'll like, get better with time as you guys implement some of this stuff pretty soon. And as we show you guys examples, it's gonna like clear up. So yeah, one more time, we have these features. We have the join month, the age, the gender, and we have to get to the prediction of whether they left or not. That's the whole problem that the client wanted us to solve. So we as in now we're the model. The model gives each of these features a certain weightage, and then we convert that into a single number by taking that weighted sum. We add up each of these products into one number at the end, and then we want another parameter that we can tweak over time as we mess up and learn again and again and again. And then we pass it through our sigmoid function to convert whatever real number at this point there is into something between 0 and 1 that we can round up or down. At this point, we have made our prediction. We assess the cost. How do we do that? We compare it to the actual truth about that data point. In that data point, if that customer, maybe like they joined in May and they're 53 years old and they're a male, then if they stayed, but we guessed that they left, we have to make that comparison, and we have to calculate the cost according to a cost function that's like, usually defined within these libraries. And then given whatever cost we have made that measurement. We have to shoot again in the dark with a new set of weights and biases to plot another value for the cost. And that's how we get that curve over time that we can minimize, that we saw on the previous slide. So we try again with the new weights and biases as new inputs. So that's when the next data point comes in. Are we good with this?
We get a question in the chat.
All right. If the data set gets, if the data size gets large enough to take a while, how do we make sure that the machine adjusts the weights as efficiently as it can to make less mistakes? So like I see kind of two questions in there. One is about efficiency. One is about effectiveness. So which one are you like trying to focus on? Efficiency would be like the computational, like steps required. Effectiveness would be the accuracy. Making it so that it doesn't take a lifetime. Okay, so more about the efficiency. What you'll find is machine learning is really efficient. And in fact, if you look at it under the hood, it's basically a couple of for loops for iterating over this many data points to learn from in the training set. And, like iterating over this many points in the testing. It's just like most things happen. I don't want to be wrong about this, but it's not terrible computational complexity. It's not horrendous. In deep learning, you do have a lot more weights and biases to tweak, and that's when it gets nightmarishly long to run it on a normal processor, which is why people use GPUs for deep learning. But if you don't know about deep learning, that's okay. All right, so
if you've ever heard about that vague concept called cloud computing, this is where it comes in.
Yeah.
So in Google Colab, we essentially use Google's own computers rather than our laptops to do all this stuff.
Right. That's where cloud computing meets machine learning. Google Colab. So what? All right, that makes sense. All right, good. I was gonna ask. Right. So Peter says, what is meant by cost? So the cost is okay. I can show you. Give me 1 second. It's a pretty complicated function. Oops, I mistyped that. Here's an example. This is log loss. All right. You basically compare the given inputs and the labels with the expected output, and then you try to penalize the algorithm with that. And over time, this value, this result essentially is what that algorithm will try to minimize, and it'll calculate the new cost with each guess. And over time, it's going to try to take steps in tweaking its weights and biases to get that cost down. Does that help? I feel like I made it worse. Yeah, it does. Okay. All right. Nice. Yep. That's exactly it. The cost slash loss function is a way of measuring how accurate the model is in a broad sense. Accuracy has a slightly different formal definition, but that's the idea. Yeah. Essentially, you can think of it in an abstract way as the difference between the predicted and the actual value, even though the math would be a little more nuanced.
We had a question from Rishi that got lost up there. He said,
Yes.
wait, each input has its own bias level, right?
Not in logistic regression, because we are trying to turn everything, all these multiple inputs, into one number. And we're adding one more number to that number before sending it into Sigmoid. Sigmoid can only do a one-to-one mapping, right? So a bias has to be a singular number. It cannot be like a vector of three numbers for each feature. We're combining all the features into this weighted sum.
Wait, okay, sorry for like asking a repeat question, but like,
That's
could
totally
you explain
fine.
what the bias is again then?
Yep, the bias is just another parameter for the log-reg model to tweak as it learns over more and more data.
Okay, cool. Okay, thank you. That makes sense.
All right, awesome. All right, anything else? Like, that was a little quicker than I anticipated. All right, we can come back at the end. But yeah, overall, how does it fit into the bigger picture, right? We start with the problem. Very important. We need to be very clear about what business problem we are trying to solve. Ooh, okay, we have some questions. Can we get to that after this one summary slide? Is that okay? All right, cool. So problem definition, we need that. We need to be very clear. And that includes something called performance metrics. And we're going to study those like later in the semester, but performance metrics are how you assess whether your model did a good job or not. And it's usually not as simple as how many it got right versus how many it got wrong. It gets a lot more complex than that. All right, so you do the data analysis and you process it, you clean it, and then you do feature engineering. Sometimes like these things overlap. Sometimes the next step informs the previous step and you have to go back and try to modify how you go about your data analysis so that your features are going to be better in the next stage. So you keep jumping back and forth over time. Yep, oops. So you start with your training data. You take your data, you split it so that some of it is reserved for testing, some of it is used for training. Then you make the model predict, it checks the cost, it optimizes by tweaking its weights and biases. And that's an iterative process, how many ever cycles you set it to. Like that's called iterations. And then how many times it goes over the whole data set, that's called an epoch. But yep, that's the whole training cycle. And then you go to testing. Once you're happy with the cost, like, it's reached as low as it goes, you go to test data and you see how it performs there. You don't give it the answers, you check it manually, like to see how well it does without the answer. And that's basically how we also learn, right? We learn by solving examples that are given to us. And then on the test, like, we don't actually have the answer. We have to arrive at it in the dark. So, and if we find that it did terrible in testing, we go back into training. So that's, and normally, like, you will hear another step in here called validation, which is like, you have training and then you have validation and then testing. But essentially the principle is that you do need to go back in if you mess up in test data. Once you're happy with test performance, you can deploy the model. And that's when your client will hopefully pay you a nice sum so that you can go and buy yourself some pizza. So that is, all right, here's some tools and websites. You guys can check these out later. But all right, so we can go back to these very nice questions. Might be random, but how much development of the hardware is needed in 2021 to do what we want to do with these machine learning algorithms? Are we close enough to the maximum speed we need to compute these things? Or is it just the more the better? Like, it's kind of both. And as far as machine learning is concerned, we have a satisfactory performance out of the hardware that we have now. But if we want to go towards like deep learning, something that's more like, real-time visual recognition, like anything that doesn't involve a fixed data set going in and just getting outputs, because those are like more manual calculations. In terms of deep learning, it's more like a real-time response feedback kind of thing. Natural language processing is an example of that. And for that stuff, we do need more computational power, even though right now we have something like Google wasn't satisfied with the GPU. So they invented something called the tensor processing unit. And you can use that in Colab. There's like some extra code you need to write to like be able to use it. But it's a step beyond the GPU's ability. But yeah, machine learning, it's not that computationally hectic, I guess. This may be something for the future, but what about classifying more than binary options? Great question. So that's multi-class classification. And what we would do in that case.
1 second. I'm sorry. So sorry to cut you off. But if you could put the link to the feedback form before we.
Yeah. I was going to get to that at 6:28. Should I do it right now? I can do it right now.
Yes, please. Because it seems like people are already leaving.
All right. Yeah, let me do that. You guys, it's going to be really quick. Just fill that out for us, please. And yeah, it's like some 45 seconds or something. All right. So going back to, but more than binary classification, right? If we have sigmoid, it's just between 1 and 0. But if we had multiple, then we would have something like, we could have it output a tensor, or really a vector, where we have like a 1 and then a bunch of zeros, depending on what class that corresponds to. Like if we had a problem saying, predict if tomorrow is going to be rainy, sunny, or cloudy. We would have a vector of size 3 as the output, and then we would take the maximum value within that vector as the answer. Does that make sense? There's a function for that called like softmax and everything. Any good traditional books on the math between classification and regression? I wish I actually read books to answer this question. If I find one, I will let you know. But most of what I do like comes from my research and the net and the coursework that I've done. All right, 1 second. There's a lot of questions in here. Hang on. Let's go back. I need to make this thing bigger. All right, wait. Thank you guys for the comments on the slides. Yes, I do try. If we have a data set to train the model, where does the test data come from? Is it just a subset of the data reserved for testing? So normally, yeah, we have a giant data set. We chunk off a bunch of it for testing, or if you want to do validation as well, which is like testing before testing, then you chunk off another part. And usually there's like an 80-20 split between how much you use for training and then how much you use for testing. But that's what, sometimes if the client isn't fully satisfied with you, they're going to give you data that you as the engineer didn't have access to. And then they'll be like, all right, try this out on this fresh new data that came in yesterday. And then if your model fails there, they'll be like, all right, I'm not going to pay you until you beat this minimum accuracy. So if we have, oh no, wait, I just did. How long does it take for the AI or the program to determine the correct weights and biases for the set? It'll probably depend on the complexity of the problem, but what's the average time / data required? That really depends on the problem. You can have tiny data sets of like, 100 data points, and that'll converge really quick. And you can just set it to run over that same data multiple times. Or you can have like something that's like 1 million entries, but it depends on the scale and the nature of the problem. I wouldn't say there's like a fixed value to that.
So when you say
yes.
When you say really quick for like the 100, like for like the 100 data set, for example, like what do you mean by really quick?
Under
like
a second.
A few seconds? Oh wow. Okay, that's
But
interesting.
yeah, but if it's deep learning, then it's gonna be like way longer than that.
Right.
So
Okay.
in
Thanks.
machine learning, it's really pretty quick. Um, Introduction to data science. Yes, that is one class that I'm taking right now. There are classes that will be in next year for most of us, which are Intro to ML, Intro to AI. There's a deep learning course. So yeah, does the project we are going to be working on use logistic regression? That is, yep, that's correct. For something radiology related, like detecting a cancer cell or something like that. All right, so that's actually the well, somewhat similar to the problem that we had last semester, where we were using deep learning neural network to classify whether a cell was infected with malaria, and so that one actually took a good 4 minutes for 5 epochs over about 14,000 images, if that gives you any idea. It's pretty fast. It really is. Where these things slow down is when you have huge models. There's one called BERT, and that really operates on like massive data in order to learn to like compute what's being said in an audio file, or what's being said in a tweet, right? So like something as big as that would take a ton of time to train, but employing it for testing is really simple. Have we covered the specifics of a project yet? No. We haven't gotten that far yet. Don't worry, we are still like in the very beginning stages of what we have laid out this semester. Do we have a YouTube playlist of the recordings? Yep, we have the YouTube channel. You can find it in the Discord channel for the YouTube channel. Yeah, we will share that with you. Sidesh, did you want to say something?
No, I'm fine.
Okay.
You don't have a
Yeah.
playlist per se, but all the videos are up there.
Yes. Will we cover deep learning stuff in the future? You can like go back to some of the stuff from last semester if you want to do it on your own. But yes, in the future, we will revisit maybe another area of deep learning. Last time we did computer vision using convolutional neural networks. We might do like maybe NLP or something in the future. That's another area of deep learning. Yes, it really is. It's super fun.
Like I had something to say regarding the like computing time and like
Yep.
the questions regarding that.
Go ahead.
So it really depends on how the model is laid, how much data you have, what type of data you have. And like last year I worked on a model. It took me 4 days to train it. It was like I guess it was trained on a couple of thousands of parameters, and it had like 5,000 images or something like that. And it also is a constraint of how the processors are in the industry. So right now we pretty much have like a 10 nanometer processor, but slowly the industry is moving towards the 5 nanometer and the 3 nanometer processors, like the Apple M1 chip. So that will significantly improve the performance and thus help us train faster and learn better, I guess.
All right,
Yeah, it's
well,
like,
there you have it. Moore's law
yeah.
go blur. Yep. Channel says and 8 nanometers. I know next to nothing about this stuff, but you can trust these guys because they actually like
Yeah,
they're
it's
smart.
AMD's 8 nanometer ones, the new ones.
Yeah, AMD. Dang.
Ryzen.
I think my brother has that. Who's leading the hardware industry right now? You guys.
I would say Apple.
Nice.
Yeah, definitely. 5 nanometers.
By the way, we're officially done. If you guys just want to like hang, chill, and ask questions or something, yeah, feel free. Otherwise, we're formally done. It's 6:31.
In terms of cost effectiveness, definitely AMD. And I guess Intel is just holding back its research and just getting ears on its old processors.
Don't forget about Qualcomm, my guy.
Qualcomm isn't like too much into computing right now, like the mainstream computing. It's like on mobile processors and all.
That's fair. Yeah, I did an essay for my business class in 12th grade about Qualcomm and how their whole industry is kind of like changing in multiple angles. Because like a lot of these mobile phone manufacturers are making their own chips in house, which is a big factor in their whole business model.
We are too. We are too.
I was surprised we didn't have one already when I came
Mhm.
freshman year.
All right. Thank you, John.
Thank you guys. See you next week. Same time.
Chabi's in the next room. He's still on the call. Chabi, you want to come in here? We can stop recording, I think.
Hey, what's up?
Oh,